Now to the selection of the equivalent on resistance of the switches S1 and S2. The equivalent on resistance of the switches S1 and S2 are typically selected so that the efficiency of the series resonant pulse inverter is larger than 90%. The efficiency is given as the ratio between the power that's delivered to the load divided by the input power. And the input power can be rewritten as PRI plus the power losses that happens in the converter. And these power losses originate from the current that's flowing in the switch's equivalent on resistance, RDS1 and RDS2, as well as the resonant current that's flowing in the equivalent series resistance of the inductor, the equivalent series resistance of the capacitor. So all these resistors introduce conduction losses that basically increases the input power than the power that's delivered to the output AC node. So let's try to find the power loss first in the equivalent on resistance of the switches RDS1 and RDS2. Well, we mentioned the current in one of the switches, say in IS1, is going to be equal to the resonant current in the first half cycle. So when omega t is between 0 and pi, and in the second half cycle is going to be 0. And basically, if we perform the integration to find the RMS current or the RMS value of the current in S1, we should define it as the average or the mean of S1 current we'll find it basically equal to Im square divided by 4. And so the RMS current in S1, square, is equal to Im divided by 2. And similarly, the RMS current for the bottom switch will also be Im divided by 2, where Im is the amplitude of the resonant circuit current. And so the conduction loss in the switches is called PRDS, will be the conduction loss that's happening in the top switch plus the conduction loss that's happening in the bottom switch, which is equal to 1 over 4 Im square, the RMS current square, times RDS1 plus RDS2. And if we assume that we are using identical transistors for S1 and S2, then they will have the same RDS value. And so this expression will give us 1 over 2 Im square RDS, assuming we are using identical switches. So RDS1 are identical transistors, RDS1 is equal to RDS2 is equal to RDS. Now, we need to also calculate the losses that happens in the series or the equivalent series resistance of the inductor, as well as the equivalent series resistance of the capacitor. And that's very simple because we already know the resonant current as Im sine omega t minus psi. And so the RMS value of this current is sinusoidal current. Its RMS value will be just the amplitude Im over square root 2. And so the power loss that will happen in RL will be 1 over 2 Im square RL. And similarly, the power loss that will happen in RC will be 1 over 2 Im square RC. So if we add all that together, we get that the total conduction loss in the series resonant converter is going to be 1 over 2 Im square RDS, assuming identical switches, plus 1 over 2 Im square times RL plus 1 over 2 Im square times RC, which can be rewritten as 1 over 2 Im square, if we take it common factor, RDS plus RL plus RC. And in a previous video, we defined this addition or the sum of these three resistors as R small. So it's equal to 1 over 2 Im square times R small. Now, this calculation doesn't take into account the conduction loss that happens in the parallel diode, either the body diode of the employed transistor or an explicit diode, anti-parallel diode that's connected across the switch, just for simplicity. And so, for simplicity, a simple and a first order expression for the efficiency of the converter, which is the ratio between the power that's delivered to the AC load divided by the power taken from the DC supply, which we said can be rewritten as PRI divided by PRI plus the conduction loss that we just calculated. The power that's delivered to the load is the RMS value squared of the resonant current, right? The resonant current is essentially the current that will flow in the load resistor times Ri. That's the power that's delivered to the AC load. Then we have 1 over 2 Im square Ri plus the conduction loss, which is 1 over 2 Im square times R small. So we can cancel this with this and this, and we end up with Ri divided by Ri plus R small, which can be rewritten as, if we divide the numerator and denominator by Ri, we'll get 1 plus 1 over 1 plus R over Ri. By the way, in a previous video, we also called Ri plus R small is R. Okay. So two things here. This is a first order approximation for the efficiency because, as I mentioned, the conduction loss doesn't consider the losses that happens in these anti-parallel diodes. Also, the efficiency doesn't include the switching losses due to driving the gate capacitance of the switches, the output capacitance of the switches as well, if we don't have zero voltage switching, as well as the reverse recovery losses in the body diode or anti-parallel diode. So this is a simplified expression as a first order expression. Now, an important parameter for a series resonant converter, as we said, an inverter is basically, or a DC to AC converter, it takes DC voltage and produces sinusoidal voltage, AC voltage. That's a DC to AC converter. And so an important parameter is the voltage transfer ratio, and it's defined as the amplitude of the generated sine, it's called Vm, divided by the input DC voltage, so V capital I. Well, we know that we calculated before the voltage in the resistor, in the load resistor, this resistor, will be the resonant current multiplied by the load resistance Ri. And we know that the resonant current is given by its amplitude 2Vi divided by pi r times psi times the load resistance sine omega t minus psi. Okay. So the amplitude of the output voltage is given by this expression. And so the conversion ratio M, we just divide the amplitude Vm that we just calculated by Vi. So we get, sorry, this is cosine psi. We get 2 times cosine psi divided by pi multiplied by Ri over R. Okay. And so this ratio, we just defined it in the previous slide as the efficiency of the inverter. And so we get 2 cosine psi divided by pi multiplied by the efficiency, M. Okay. So an interesting observation here, if we try to plot the voltage transfer ratio versus frequency, we'll find that at resonance, the center frequency of the series resonance circuit, cosine psi is going to be 1. So we'll get a peak value that's 2 over pi multiplied by the efficiency. And the efficiency, we said, is typically larger than 90%, so 0.9, larger than 0.9. So the efficiency of the converter is important because it essentially, the lower the efficiency, the lower the generated amplitude of the AC output voltage. And then as we deviate from the resonant frequency, we have a cosine psi here. So basically we have a response that looks like this versus the frequency. Now, one observation here is sometimes we would like to control the amplitude of the produced AC output voltage. And to do that, what can be done is to control the switching frequency of the half bridge, so we deviate from the resonant frequency. Of course, typically we operate above the resonant frequency so that we enable zero voltage switching, but that's a little advanced. But anyway, so as we deviate from the resonant frequency, we'll find that the amplitude of the output voltage is going to decrease, right? So that's one way, controlling or tuning F around the resonant frequency to control the amplitude of the amplitude of the generated AC output voltage. That's one observation. The only issue in that is if we are at a specific frequency, say this frequency, and the load resistor Ri has it changed. So what will happen is, we know that the quality of the series resonance circuit is basically depends on the resistor Ri, right? So it's given by omega node L divided by the total resistance R, where R includes the load resistor as well as the equivalent series resistance of the inductor and capacitor. And so as we increase, or as Ri changes in value, R is going to change, the quality is going to change, which basically the bandwidth is going to change. And essentially what we'll have, we'll have maybe, if Ri increased, the response will look something like that. So what will happen is, while the frequency is at this particular value, and at Ri1, the conversion ratio is given by this value. Now, when the load changed, we have this response for Ri2, and so basically the output voltage increases in value, say if Ri increased in value, and vice versa. So the point is, if we're going to change the frequency, it has to be via a closed control loop, so that as the load changes in value, as the load resistor changes in value, we can track that and modulate the frequency to compensate for these changes and maintain the amplitude of the output voltage at the desired value.